If everyone is ready, we're gonna start the second part of the session on time-dependent and independent approaches. So the first talk of this session is by Bruno Senjean, and he will talk about quantum computing applied to quantum chemistry.
Thank you very much. So thank you for the organizer for letting me the opportunity to present my work today. I have been asked with a kind of introduction to quantum computing applied to quantum chemistry. So for the ones who have been there last week, it will be not trivial, but a reminder. And for the one who couldn't attend the meeting, I really tried to go to the basics first and present mostly the two main algorithms that are used in quantum computing, especially applied to quantum chemistry. So this is the outline of my talk. First, I will give a general introduction, mostly on quantum computers without talking about quantum chemistry. And then we will see how we can really use them to solve the many-body problem in quantum chemistry. If I have time, normally I should have time, I will present the extension that we are working on in Montpellier with my colleagues, and also with some collaborators in Strasbourg in the laboratoire de chimie quantique. So let's start with the problem that we want to solve. Of course, we are interested about the electronic structure problem, in time independent problem. So we have the Hamiltonian that we will usually write in second quantization. And we want to extract the eigenstate and the energies, so the eigenvalues of this problem. This second quantized Hamiltonian will be actually transformed into a qubit, what we call the qubit Hamiltonian, using the Jordan-Wigner transformation. And the main limitation step in quantum algorithm will actually be this scaling. It's the number of terms in the Hamiltonian that you have to measure independently. But I will come back to that with more precision later on. But if you don't have a quantum computer, well, if you want to solve this problem, you have to express it in a many-body basis. And this many-body basis, if you represent it with the occupation number representation, you can write it this way. So this will be a Slater determinant. And you have the occupation of each spin orbital of your system, which can be the 0 or 1. And if you don't conserve the number of particles, if you really consider your full Fock space, you will have 2 to the power of n many-body determinants. Right? So your wave function will be returned as a linear combination of exponentially many numbers of Slater determinants. And this is what we call the exponential wall problem. And obviously on a classical device, we cannot solve that efficiently. So there are, of course, many solutions. We, since many decades now, either we can just truncate these bases, so we can consider configuration interaction methods, coupled cluster, or other type of techniques. There are also embedding techniques that are mostly used now also. So just to get the best subspace that still represents your problem in an efficient manner. Or the subject of this talk is the quantum computers, which can actually describe all these states with all these many expressed in this many-body basis, the exponentially many number of Slater determinants, but in a polynomial cost. There are also other techniques that are used, other paradigms using, for instance, the electronic density or reduced density matrices instead of the wave function, like we usually know the density functional theory, for instance. And if I have time, I will present some results about that also later on, connected to quantum computing. So quantum computers, what are they? And why are they useful to solve the problem that I mentioned? So first of all, the quantum computers has been introduced by Feynman in the early 80s. Well, Feynman just said, okay, maybe to solve a quantum problem, we need a quantum machine. He was mostly thinking about simulating a problem with another quantum problem. The one I'm talking about today is not a simulation of a physical problem with a quantum computer. It's really a calculation, a computation that we can do with a quantum computer. It's a bit different. We are not really simulating a problem. We are trying to compute the properties of this problem using gate-based quantum computers. And typically, those quantum computers will be composed of qubits, quantum bits, that are quantum, so they take advantage of the superposition and the entanglement, so the quantum mechanical law. So a qubit can actually be represented on a block sphere, and it's a superposition of two states, 0 and 1, in comparison to a classical bit, which is either 0 or 1, but not a superposition of the two. And now, if you consider several qubits that can be entangled together, you now have a superposition of 2 to the power of n possible states, where n is the number of qubits. So indeed, if one qubit is a superposition of 0 and 1, if you have several qubits, each of them can be in this superposition, and entangled together, they really create an exponential number of basis states. Those basis states are actually described by bit strings, so a combination of 0 or 1. And so if you need to encode this state on a quantum computer, you can actually do it on only m qubits, in contrast to an exponentially many number of operations on a classical computer. And I just would like to stop here with this expression. You see that it's really the same as the one I described here, the many body problem. So we already see the connection between quantum computers and quantum chemistry. But how can we really map these? We will see that in the next slide. But first, let's see how a quantum computer works. So if I want to construct this state, for instance, it's a linear combination of all possible bit strings generated by 3 bits. So you have 8 combinations possible, 2 to the power of 3. On a classical computer, you will have to treat each of those separately, get an input, do some operation, and get an output, which is also classical, so only 3 bits of information. On a quantum computer, with the quantum bits, you can really describe those 8 combinations at once, like a single step. And then your quantum computers will make some operations with this combination, and you will have another output at the end. And then you measure and you will have a collapse. Let's see. So this equal superposition of all the bit strings can actually be prepared with 3 qubits. So normally we start with the state 0, and then we apply some gates. So here it's Hadamard gates. It's a single qubit gate which creates an equal superposition of 0 and 1. And so if you apply it to each qubit, you actually create this state. It's really simple to do. And then you can apply other type of gates. It can be 1 or 2 qubit gates, which will entangle your qubit together and will change the coefficients in front of all those bit strings, all those configurations that you have. And of course, we want to control it. So that's really the difference really between just simulating your problem on a quantum computer or really trying to measure some properties. So we really want to control every step and get all the coefficients that we want in this equation. And once you apply all those unitary 1 and 2 qubit gates, you have another state here that in this example is only a combination of 0, 0, 0, 1, 0, 0, and 1, 1, 1. And when you measure, you have the collapse of your state. So you only get the classical information at the end. And this classical information is one of those 3 bit strings with a probability that depends on the coefficient in front of this configuration. And so if you want to have actually access to those contributions, you have to do the measure, and also do the full circuit and measure it many number of times to accumulate statistics. It's really different from a classical computer. It cannot copy data because of this collapse. It has really much higher error rate, so we have also to deal with that. But still, we can encode a many-body problem with only a linear number of qubits with respect to the system size. So how can we really put a quantum chemical problem onto a quantum computer? One of the most well-known mappings, but that there exist also others, is called Jordan-Wigner. And it's simply a one-to-one mapping between the occupation of a spin orbital and the value of your qubits, the state of your qubits. So this is exactly the same expression that I wrote before, where one electronic configuration is actually written as a bit string in the occupation number representation, where you have 0 for a non-occupied spin orbital and 1 for an occupied spin orbital. So the number of qubits actually correspond exactly to the number of spin orbitals in your problem. And so this is how to encode the many-body basis into your quantum computer. But now we also want to measure the Hamiltonian, to apply the Hamiltonian. And how to do it on a quantum computer? Well, we have to apply some unitary operations, and we want to describe the second quantized Hamiltonian. So we can just transform the creation and annihilation operators as a tensor product of Pauli strings, of Pauli matrices. So the identity X and Y Pauli string, Pauli. And then a sequence of Z gates that are actually here because the problem is fermionic and we have to encode the anti-commutation rules. If your problem is bosonic, you wouldn't have the tensor product of Z gates. So this is the qubit Hamiltonian that we have. So in second quantization, this is the fermionic Hamiltonian, and it's exactly the same in another form, thanks to the Jordan-Wigner transformation, where you have a linear combination of Pauli strings. So Pauli string is just a tensor product of Pauli matrices, and thanks to this relation. And this, each of those terms are unitary, actually. No. Yes, they are unitary. You can apply them, measure them on the quantum computer. So there exist different kind of algorithms to do that. The most well-known that has actually been developed in the before the 20th century is called phase estimation, quantum phase estimation. And we can measure, we can apply a bit unitary and measure the phase. So if the unitary is the exponential ht, so the propagator, then we can actually extract the phase, so the energy times t of your problem. So this algorithm works in two ways. We have two registers of quantum bits. One is called the ancilla register, and the other one encodes the problem. So if you have n spin orbitals, here you will have n qubits. And the second register will actually allow you to measure the energy with a given accuracy. More you have ancilla qubits, more accurate you will be. The only requirement for this algorithm to work is to have a non-zero overlap with the eigenstates. So you have to start your problem here, your register state, with a state that has a non-zero overlap with the eigenstate you are interested in. For instance, in chemistry, this will be the Hartree-Fock state. The Hartree-Fock state can be written as a linear combination of the eigenstates, usually with a large overlap with the ground state of your problem. That's the difference. How your problem is strongly correlated. So how does it work in more detail? The first step is to apply a Hadamard gate to create a superposition on all your ancilla qubits here. So this is how the state will look like. So you have a tensor product of all superposition of each state for the qubits here. That's the point of the Hadamard gate. And also you have your register that is the Hartree-Fock state here, which can be written this way. This is the final state here of the blue box before applying overdose. And the K are just the integer representation of the bit strings of the instructions. Okay, up to here, we don't really know what to do with that. But if we apply control unitaries, where the unitary, if I remind you, is exponential IHT, if you do those control unitaries on the ancilla qubit, we have what we call a phase kickback. And we see this phase kickback actually appearing in the state. And so this is the state that you obtain after all those control unitaries on the ancilla qubits in the registers. Here, what you can recognize is actually a kind of Fourier transform expression. And so if you apply the inverse Fourier transform, so this can also be decomposed into several quantum gates, and we know how to do it. You end up with a state like this, before measurements, this stage. So this state here is the binary string representation of the value of your phase, of your energy, and it's the state of the ancilla qubits. And those other eigenstates are actually still those ones, the registers. And then you measure. And of course, when you measure, you will actually collapse this state. So you will have a probability AJ square, which is actually the overlap between the eigenstates, this eigenstate, and the artifact state, for instance, if you started your algorithm with the artifact state. And so you have this the probability AJ square to get the energy in the phase EJT. And also, because you have entanglement, your register here will collapse to the true eigenstate psi j. You can, of course, do this operation several times, and you will get, because it's not deterministic, you will get different probabilities of getting other eigenstates if you want. And so by repeating this several times, normally you should extract all the spectrum of your problem. Okay, but that actually, this phase estimation algorithm is much too complicated in terms of circuit depth. Applying all those unitary operations controlled on all those ancilla qubits is extremely long. It demands too much operations, and because of quantum decoherence, it just cannot be done right now. There are several very small experiments on this, but really it doesn't scale pretty well with the current devices that we have. But still, it is known to be one of the best algorithms in the world. So another way to deal with the noisy quantum computer that we have, so this is called the NISQ era, where NISQ is a noisy intermediate scale quantum. In this noisy era of quantum devices, one other type of algorithm that is always used is the variational quantum eigensolver. And this one is actually a hybrid algorithm between a classical one and a quantum computer. And it allows to have much shorter circuit depth, but at the expense of doing much more measurements. So it's actually not efficient, but for the current device that we have, it's doable. So we can do that. So this algorithm is based on the variational principle, where you have to minimize it with respect to trial wave function, depending on some parameters. You will minimize the energy, which is computed as a summation of the electronic integrals times the expectation value of all the Pauli strings that defines your qubit Hamiltonian. So let's see how it works. Imagine you have your interacting problem here. You first do an initialization, so you can define the artifact state here, for instance. Then you will apply what we call the NZATs, which depends on several gates. So in general, in chemistry, we use the unitary coupled cluster NZATs. So it's just the unitary version of coupled cluster that we know in chemistry. And the amplitudes of coupled cluster here are the theta parameters that needs to be optimized. Then we have some post-rotation and measurements to measure the Pauli strings of your problem and to measure the energy. And once the energy is measured, well, the classical optimizer on a classical computer will give you a new set of parameters, and you do that ever again and again until you minimize your energy, and hopefully you get close energy to the ground state. Okay, so that's the two main algorithms that have been developed so far in quantum computing. There have been several extensions of them as well, but here I would like just to give you some examples that we have done in Montpellier. Very fast with not much details, but just to see what we can actually do. So I showed you that we can extract the energies, but that's not the only thing we are interested in chemistry. We are interested in molecular properties, energy gradients. We are also interested in the excited state, and we have seen that EQE is the variational quantum eigensolver because of the variational principle was aimed for the ground state only at the beginning. So we would like also to extract excited state energy, excited state gradients, coupling between the excited states. Also very recently, we have looked at the quantum advantage to do density functional theory. So molecular properties, derivative of the energy with respect to an external perturbation or a change of coordinate if you want to do geometry optimization. This can be done quite simply. We can take the electronic integrals and the analytical derivative, for instance. Then we encode the problem on a quantum computer, Jordan did now. Using the variational quantum eigensolver, we can measure the expectation value of the Hamiltonian. And due to the Hellman-Feynman theorem, we can actually have the first estimation of the first order energy derivative with the nuclear coordinates. And so you can do geometry optimization, for instance. And if we want, we can also extract higher order energy derivatives. So in the paper that we published 3 years ago now, we use the V3-based algorithm and also a Q2, so quantum phase estimation based algorithm, to extract higher order derivatives like this using the sum over state formulas. So we extracted excited states and we recompute the second order energy derivative using this sum over states. So all of this can be done. So we have done it actually in Delft at the time when I was in the Netherlands on a true quantum computer. It was only a 2-qubit device, and we did the geometry optimization on the hydrogen molecule. So very small system. But we wanted to see if the quantum computers could really do the geometry optimization. So we have the exact solution, full CI solution, in the minimal basis. And all those red lines, for instance, and the blue arrows represent the gradients direction that we have computed. And we can see in the vertical lines the geometry optimized, the optimized geometry that we got at the end. So in full CI, compared to full CI, we have an error that is very small. But if you look at the energy, so in blue here, or the dot in red as well, it's really not good compared to full CI. That's because we have a systematic error. I mean, in quantum computing, we have a lot of different errors, depolarizing noise and stuff like this. So achieving full CI is not easy. But still, in terms of geometry optimization, the tendency of the curve was the same. So we could achieve a very good accuracy for we also computed the polarizability, for instance. So the second order derivative of the energy with respect to an external perturbation of the electric field. We have the R34 presence in red, the exact one in blue. So we see that R34 is fading from actually when we increase the length of the hydrogen molecule. And the experiment was in yellow here. And first, we were really surprised because when we increased the bond length, it was getting completely wrong. We didn't know why, because the other energies were correct. A bit surprising. But actually, that's a kind of artifact because H2 in a minimal basis, you have 4 spin orbitals. So you should need 4 qubits to represent the problem. But we only had 2 of them. For the energy, it was not a problem because we could actually, with some symmetry condition, go to 2 qubits only. So we did the experiment with 2 qubits. But when you add an external perturbation of the electric field, you actually break this symmetry. And so 2 qubits were not sufficient anymore to describe the problem. And so we verified that by doing the projection of the exact solution to the 2 qubits subspace. And we found the same results as the experiment. So indeed, that was the problem. We broke the symmetry due to the external perturbation. We need to have 4 qubits. Another thing we can do is to find excited state with the variational quantum eigensolver. And to do that, we can consider, instead of just doing the ground state variational principle, so the Rayleigh-Ritz variational principle, we can use the ensemble generalization of this variational principle, which goes to the and so it's just a summation over all the states that we're interested in, the states time. So we have a weight here, W, of those states, and you can prepare all of those states on different quantum computers, or the same quantum computers, but just different states. So for instance, this is the V3 that I showed you before. Nothing changes. You prepare our Trifoc here, and you do your unitary quantum cluster. But on another state, you will prepare an initial state that is also simple to do, but which is orthogonal to the Trifoc state. So it can be a doubly excited configuration or a singlet excited configuration. And so those states are orthogonal, and you apply the exact same unitary on those states. So you conserve orthogonality. And instead of minimizing the ground state energy, you minimize the ensemble energy. And by virtue of the variational principle, you should get the ground state energy here and an excited state energy here, orthogonal to the ground state. And it should be the first excited state. Okay, so this we have also applied on a simple problem, which is the formaldehyde. And the formaldehyde, if you look at it, we froze every coordinates except the dihedral angle and the bending angle of this hydrogen. And we saw that there was a chemical intersection, and that was we were looking for. Actually, we wanted to reproduce this, this very nice. And I will just show you one cut of this potential energy surface. So this is the plan in gray. And this is what we obtained. So doing the state average, so ensemble variational quantum eigensolver. And here in red, we have the state average complete active space self-consistent. And indeed, we are really close. Well, we are on top of the curve given by the state average complete active space self-consistent. This is not done on a real quantum computer. This is a state vector simulation without nodes. That's why we are on top of the curve. Otherwise, it would not be. But what we found, and this is of very big interest at the moment at the Institute, is that if you see the triangles here, they follow the same nature. The states follow the same nature. It looks like we have actually diabatic states and not adiabatic ones. From what I heard, this is of very nice interest for the dynamics to do excited state dynamics. And so we are currently looking with Benjamin Lazare, Neil Montpellier, if this state average algorithm on quantum computer could naturally get diabatic states and not or quasi-diabatic ones with, let's say, no cost. Okay, and last example I wanted just to share with you is a work that we did on density functional theory. So we know that quantum computer can solve the full CI problem with a polynomial cost. And also we know that DFT can also solve in principle the ground state problem here with also polynomial cost. But can we use quantum computers to speed up the DFT calculation? That's not obvious because the DFT problem is not exponential. So the scaling, but we still wanted to look at that. I'm not entering to the details because of time, but we could map the DFT problem efficiently with only a logarithmic number of qubits compared to the size of the problem. So if you have n particles, you can actually describe it with log n qubits. So we hope to have a quantum advantage with that. And this is what we got on the simulation on a quantum computer. So on the 8 hydrogen chains, for instance, you have the full CI results here in blue. So this is again a minimal basis set with the LDA functional DFT. The other blue curve. And we did the quantum DFT without any noise. So just showing that our algorithm is correct. And then we added sampling noise. So as I said, when you measure the quantum computer, you just get one single bit string. So it doesn't give you any information. So in the algorithm, you have to repeat the operation a number of times, many number of times to get actually the expectation value for. So we repeated the experiment 10 to the power 5 times or 10 to the power 6 times, just to get an estimation of the sampling noise error. And this is the typical error that we get. So the error due to sampling noise is in blue and in orange here. And the error due to the RT exchange correlation functional in DFT is in blue. And what we really like actually with this is that the sampling noise error is approximately 1 order of magnitude below the RT exchange correlation functional error, which means that we maybe do not need to achieve chemical accuracy compared to the other algorithm, wave function theory. And we are maybe fine with this sampling noise error if we want to do DFT on a quantum computer. Okay, so let me just conclude on this presentation. So I wanted just to show you what we can do in a big picture with quantum computers. So in principle, we definitely have a quantum advantage. In practice, of course, this is definitely not true yet, except in some very specific problems as Google showed a few years ago. And so in practice, we need a lot of improvements experimentally and also theoretically to reduce the number of measurements, reduce the circuit depth, define new kind of algorithms, etc. And so I will try on Thursday evening to show more the challenges really that we have to achieve on quantum computing to deal with the problem that we are all interested in. I'd just like to thank Sadia Lou, my main collaborators postdoc in Strasbourg, and Mathieu Soubaner and Benjamin Lazorne in Montpellier, and Emmanuel Fromager in Strasbourg. And you, of course, for your kind attention. Thank you very much.
And I have a technical question about operational quantum eigensolver that you use to estimate the ground state energy. So it's about so the parameter theta. And because so you use optimal control at the end to estimate. So the classical computer use optimal control to estimate this minimum of theta. So it's my first question, or it's.
No. So first we measure the energy on the quantum computer, and then we can use any kind of classical optimizer that exists in the literature, gradient-based or gradient-free, Kubila, EFGS.
It's a vector theta.
So this vector theta, if we use unitary coupled cluster, is quartic with the number of qubits.
Okay.
To the power 4.
Okay, so it could be, so the dimension could be very large. And
it can be very large. In principle, actually, and that's why it is not the best algorithm that we don't think now we don't think that we can have any quantum advantage, because in principle, if you want to solve an exponentially difficult problem, you need a
okay. So I know a paper by the group, so from Princeton Rabbits, and where they propose to use optimal control in this case. So it's and to map, so basically and to time-dependent control.
Okay.
Okay, and
so
maybe something, and then we can use all the techniques that have been developed. So maybe to improve, or maybe not, so this optimization. So it's
okay. Yeah,
maybe,
I definitely would like to learn more.
okay, and so my second question is about the physical meaning of this parameter theta. So it's just a parameter. So in order to parameterize the unitary gate, or so?
So actually, here actually there is different unitary coupled cluster answers. There is the qubit based one or the fermionic unitary coupled cluster. So let me talk maybe more about the fermionic unitary coupled cluster, because that's how we think of it usually as a police. You can just imagine those parameters to be the amplitudes associated to the fermionic excitation of the cluster answers first. So there is a physical meaning.
Okay, thank you very much for that nice talk. I have even more devising about those possibilities of various algorithms to try to how a computer could work and could be or, as you said, there is a little one that you made this H2 calculations. So my point is that what do you use to solve those things? Do you use a machine which is kind of simulating a quantum computer? Or
let me first say that there are quantum computers.
yeah, there are a few. No, there are a few. I agree with you, but on the daily basis, what is your methodology to try to test all those kind of hypotheses? So technically,
Yeah.
what's the machine that you have on your desk or somewhere else?
I do it on my laptop or on a cluster, and it's using libraries that have been developed either by Google or by IBM or also Atos, for instance. So it's all the libraries that allows you to define your qubits, to define your ansatz, to define the measurements that you have to do. So we really have each operation that should be done on a quantum computer is done on the classical one.
Yes, okay.
But it's really a full simulation of it. Like we are not cheating or anything.
Yeah,
We are
yeah.
not just representing the full matrix U. We are really dividing this matrix U into several gates. Each of those gates are a matrix, and we do it sequentially, etc. So we are really, I mean, if you want, I can change just one line in my algorithm, and it can run on a quantum computer of IBM.
Yeah.
So that's really not.
No, no,
It's really the real simulation. Yeah, but
so this is interesting.
in some papers, even when I read them, I'm like, I'm actually not sure if they are really simulating correctly or just doing the matrix problem, implementing big U and saying it's okay. But implementing big U is actually not correct because you have totalization, you have a lot of different things that apply on the quantum computer that needs to be taken into account. That's not so clear in papers. They do it on.
Still, according to me, you're talking about these various simulators that either the one of Google or these machine and so on. Are they open?
No, Google
Yeah,
is not.
particular.
Google, as far as I know, Google is not. You have to collaborate with them or to see with them if they are interested about your work. Otherwise, Atos machine is accessible, I think, but it's a simulator. It's not
Yeah.
but they have some stuff like model, the noise model of some true quantum computers that they have is not free. So yeah, some stuff is free, some stuff is not. And IBM, they have a cloud of several quantum computers that are free as well, but the latest ones are not free.
Thank you.